our profession as an occupational hygienist. Um, in many ways, it's lessons learning about how can we go beyond our workplace and contribute globally in improving occupational hygiene. And Stephen has been doing that for many years now. He has a Master's of Science in Environmental Chemistry, Industrial Hygiene, and he's also CIH. He has done considerable amount of research work for the dust and elemental composition in the workplace atmosphere. This is the area where it's a learning opportunity for us, including for myself. He has more than 15 years of experience in IH, an expert in different ISO and European working group, mainly focusing on uh, Belgian. He's part of the Belgian Occupational Hygiene Society. He's responsible for the training program organized by different organizations. He has been recently in Egypt conducting a training program. Member of the Belgian High Court for the Prevention and Protection of the Work, and Belgian representative for the EU platform, co-chair of the Occupational Hygiene Training Association, which is where we have been interacting. He's also past chair of the International Affairs Committee, where also we have been interacting, and uh, uh, active member of IOHA. He is recipient of several awards, including the 2022 YANT Award and recipient of 2020 ASTM D22 Award for appreciation of the work he did for organizing the conference on metals and metalloids. That's an outstanding contribution in the specific areas of metals and metalloids, but to overall occupational hygiene also. Stephen, it's great to have you, and thank you so much for taking time. I know you have lots of responsibilities and finding time and you can see that this is reaching out to so many people around the world. So we appreciate very much. IOHA appreciates very much, and the floor is yours.
Thank you. Thank you very much, Maharshi, for this. Well, it's always difficult to do short introductions if you have a lot of things to say, of course. But yeah, thanks for the introduction, and well, for sure, also the opportunity to present this. Well, I think one of the things that I definitely want to say is I'm quite a bit biased, maybe, because I'm currently, well, from this year on for the next 7 years, chairing the subcommittee on workplace atmospheres at the International Standardization. So I'm a bit biased and standards, and you will see that in my presentation, definitely. And well, I hope you enjoy it. It's not really a case study. It goes, let's say, beyond, let's say, exposure assessment for metals, metalloids, and so on. And I will end with a little bit on controls and what other organizations like the International Council on Metals and Mining are doing for controlling exposures. So, well, first of all, what I want to highlight is a sort of history in particulate sampling, and because I think it's very important that people know that, and also it will give some guidance on what I will talk about today. And so if we really look back from the, let's say, 18th century, I think everyone knows that story from Ramazzini, who identified, okay, if you inhale particles and they contain metals and so on, you get sick. And that's the I'm probably unmuted. Okay. And then you see from the early 1900s, people start measuring exposure. And, well, it took, let's say, more than 80 years, let's say, to have all our samples developed for gravimetric analysis. And this is a really important thing if we move forward in this presentation as well, and because many people are still combining, let's say, gravimetric analysis with metal analysis and so on, and this will have a certain impact on how we move forward. It is only since the 90s, so that's now 30 years ago, that we actually have internationally agreed conventions of, let's say, exposure to particulates, which are the metals part of course, and all metalloids. And it is since then that quite a lot of, let's say, things happened and moved forward in the assessment. Of course, how do we move forward? What is today and the future? Well, one of the things that I investigated, this was mainly work done because of the research at the European Commission for limit values for nickel and nickel compounds, that I tried to find out, how many samplers are actually used for measuring nickel and nickel compounds. So, well, the main issue is, and you see it here, I found out that we used 29 different sampling systems with 6 different collection substrates and 23 different analytical procedures. Well, I cannot, well, this sentence is already saying enough, how we have to approach data sets. Because, if people think that we can do exactly the same with all those different, let's say, sampling system, collection substrate, analytical procedures, I think we have to admit that, something needs to be standardized. So, well, what else do we see in the meantime? In the meantime, I mean, even when we are having not really standardized approaches for measuring metals and metalloids, well, people are already showing up at workplaces with real-time detection systems. And well, it worries me a bit, because if you haven't validated the former step, it will be really difficult to validate this one. But we need to be aware that this is also what is going on today. And I will come back to that a bit later in the presentation as well, how it is influencing a lot on the way we're dealing with, let's say, controls and so on. So here you see, again, I will talk a bit about, a lot of, let's say, standardization work that is going on. So there is like a European normalization projects on low-cost sensors, and also, medium and expensive sensors, how they are operating if you measure particles. And we have also in Australia an international sample comparison project that is going on within the International Sample Comparison Consortium that I have set up. And this is a project together with ECU University and ZCG in Australia. So, well, first of all, standardization, what, how, why? Well, I think, it's like I said in the beginning, I'm biased, I know that, but standardization is very important because otherwise, how to look at a certain result that you get. Well, you need to be aware of the fact, are we actually measuring the same thing at the end? And I hope that if I dive into, let's say, the whole sampling train, and that is what I will do in that presentation, that you have some kind of ideas what to think of before actually start to evaluate exposure of workers to metals. Well, we have mother standards. So one of the most important standards is an ISO standard, and well, in parallel, a European standard that provides you with the general requirements for the performance of procedures for measurement of chemical agents. So this is very broad. It goes broader than metals and metalloids, but it contains, all standards, let's say, that are underneath the mother standard are actually applicable if you have to follow the general requirements. So here you see a list, and we also see particle size fraction definitions, metals and metalloids requirements, and the specific determination methods. So what is the framework of the mother standard? Well, you have to classify measurements according to their purpose. And I think, many people, I hate a bit always the fact that it seems like industrial hygienists worldwide only measure for compliance, which is actually only one purpose. We forget about the other purposes. So screening measurements, and well, it's not a screening measurement as many people talk about. because screening actually doesn't really exist in the analytical world, because there is no device available that will provide you all, let's say, everything that is in your sample. That is not existing. And so let's say you need to be very careful with screening, but here it is more about screening the workplace with measurements to evaluate time weight average, variation of concentration in time and space, and comparison with limit values. And of course, the third one is the only one talking about compliance. So, well, screening measurement, well, you see, let's say that the measurement procedure have different quality perspective. So you should have sufficient selectivity in this if you use it for screening measurements. But let's say the measurement range can include a limit value, and the measurement uncertainty is well, they should have an appropriate measurement uncertainty, but it's not the main factor here. Also, for the evaluation and variation of concentration in time and space, and so you should be able of handling short measurement time, especially if you want to evaluate controls, for example. This is important. And you also have a suitable measuring range for the purpose. It's not really stated that the measurement range should include a limit value, for example. So here you're quite open. And I think a lot of those measurements, and together with the first, let's say, classification of measurements, are used mainly in, for example, epidemiological studies as well. The third one as well, but compliance measurements have very strict criteria. And here you see the strict criteria. So the average time is equal to the sampling time, meaning that you should be as close as possible of the reference period where the limit value is set. And then, you should have a validated procedure within certain ranges of the limit value you want to measure for. And of course, those things are very strict. I will come back to that later if we dive into some of the, let's say, sampling train requirements, where sometimes it is not possible to even reach those requirements. So additional requirements, you see here, if no measurement procedure meets the requirements, so you should follow a procedure with closest, let's say, performance requirements that are compared to what is used in the normal way of measuring. And your performance requirements are applicable to the entire measurement procedure, which is also in many cases forgotten. We are talking about the whole measurement procedure is sampling, transport and storage, sample preparation, and analysis. And so many people are only thinking, oh yeah, my lab is not accredited, that's a serious problem. Well, the accreditation of labs is only applicable to analysis, and we forget, well, and sometimes sample preparation a part of it, but we forget quite other important parts that should be part of accreditation in general. So for each evaluation where measurements are applicable, you should evaluate the information concerning the unambiguous interpretation of the result. You should evaluate the selectivity in the specific conditions. I will come back to that later. The measuring range, that shows you the minimum sampling time you need. That should be investigated. And you should investigate the averaging time in the specific conditions compared to your limit value and your measurement uncertainty per subsection and the total measurement uncertainty, which actually we call the expanded uncertainty. And what I see quite often in reports that I see is that only the measurement or the analytical uncertainty is included, which is quite wrong. I will show that a bit later as well. So you have some requirements on the measurement uncertainty. So depending on what kind of reference period, if you do compliance measurement, you should have, let's say, a measurement uncertainty depending on the range. For short term, it is between 0.5 and 2 times limit value, where you should have an uncertainty below or equal to 50%. And if you have long-term measurements between 0.1 and 0.5, the limit values, it's also 50%. And between 0.5 and 2 times limit values, it is 30%. Only for if you have mixtures of aerosols and vapors, you should be below 50%. And people are always saying to me, 50%, oh, that's a lot. Well, you will see that it is even difficult to go below 50% of uncertainty if you take into account each step of your procedure. So I link this with, this is only European standard, of course, but nevertheless, it is an important one because it's the only compliance standard that is available in the world, and it is referred to in many guidances. And so where you have screening measurements for the variation, time weight average, and measurement for comparison, where you see, for example, in your basic characterization, you can use quite, not very precise equipment to have an idea. If you have, your sampling strategy, time weight average concentration, you go to a little bit more accurate devices. And if you really want to comply with limit values, you follow really completely validated procedures. That is what it's saying here. So, this is what is stated in the compliance standard. So, everyone knows that you have to do a constitution of your similar exposure groups. But the second point is, as soon as you have done that, you need to investigate your measurement procedure. And, if I ask many people, if I give courses and so on, where is that paper or the written consent in your measurement procedure investigation? Well, I don't receive many answers. And I'm wondering always, if I receive an answer, it is, I asked the laboratory. Well, that is not the answer that I want. So if someone is doing an exam, when I'm in the jury, you will have problems if that is your answer. You should be able to investigate that yourself. And because at the end, you're working with the result, and you should know what the result means. So I will go very fast about the next slides, because this is, if you do an investigation, you need to follow the hierarchy of methods. And, there is in many legislations even written that you have to follow a hierarchy of methods. So the first one is probably, if you have a method specifically written in your legislation, well, you have to follow this one. But you will see that in many cases, this is adopted into, let's say, international consensus standards. So I also put a link into the presentation. So the presentation will be shared, where you can, use the control button and and a mouse click to go on the sites where you will find the information on the standards that are available. The second, you investigate our methods from national institutes, research institutes, and so on. So, here you see, you also have committee-specific reports. You have, from SKC, a catalog. You have the HSE on the MDHS, the INRS methods, and so on and so on. So there are quite a lot of resources where you can find certain methods. Well, the only problem is that in many cases, many of the national institute and research institutes are actually cooperating into standardization, what actually means that, if there is an international consensus standard containing many of the requirements in their own methods, that they won't update it anymore. So be aware, to use the last updated version, and also look at the last update date. And because, there are many methods that are there that are still referred to that are more than 30 years old. Well, I have to say, I'm quite sure that there is a more recent method available. Then you can use internal laboratory methods, but, you have to ask your laboratory certain questions then. Specifically, they need to pass all minimum validation parameters. They shall meet the conditions of the requirement standards, and they can be based on methods as indicated in previous slides. but meaning, if you cannot follow, let's say, the minimum conditions in the reference method, well, you have a problem and you cannot really use it. So, this is definitely my bias to standardization, where I say, you have three categories of measurement procedure. So A is, well, meeting all requirements. B, meaning that validation criteria are incomplete, but it has a potential to meet the requirements. And C, category methodologies have no potential at all to comply, which actually means this is what you need to investigate definitely for before you start evaluating workers' exposure. And if you have a category C method, you probably need to do some more work than just following what is in the method. Well, okay. So, well, this is my bias to standards, and I really have to say that I'm very strict in that, to be honest. And because, I see many reports and data sets that I have serious doubts. And especially, I review quite a lot of data sets on metals and metalloids. And I have to say that in many cases, it is not described as it should be, as contextual information. And while everything that I mentioned before is all, in my opinion, contextual information supporting the data point. If this is not available, well, I don't trust that number. That's my opinion. Well, you have limiting factors for all procedures for metals and metalloids. As I said, many of our samplers are based on an initial thought, measuring the gravimetrically dust or particles in the breathing zone of the worker. If you go, let's say, in the 80s and so on. Before that, it was more like in the ambient atmosphere of workplaces. So it's all based on that. So we have, let's say, parameters that are influencing the way, well, our sampling train in general. So you have the ambient parameters, so temperature, relative humidity, and this is of utmost importance. You will see a bit later why. The air pressure has also quite huge impact if you want to measure metals and metalloids, because the air pressure can have, or well, I say can, but it's quite sure that it will have an impact on the size separation of cyclone samplers if you want to determine, for example, respirable particles. And so if you have a deviation in your air pressure, you need to be aware of that. And that you probably are not measuring the respirable fraction, even you use a respirable fraction cyclone. Air sampling pump back pressure. And so always check before sampling. That is written in the standard as well. I'll come back to that later. With specific sampling substrate, because the back pressure will always have an impact on the particle, let's say, capture of the specific sampler. When you have a high back pressure, it will be really difficult to meet the requirements and have, let's say, lower than 5% relative difference in flow before and after sampling. So, and in many cases, I do know that there are different schools of thoughts with it. And the relative difference is in many cases determined with blank substrates, which is, in my opinion, a bit, well, strange. Because, if you have 5% deviation in your sampling train with blanks, it means that your pump is broke and you probably have to throw it away. And so, in my opinion, you should do that with the same sampling train you started your sampling with. So air sampling pumps, this is, I go through the whole sampling train. And so the sampling pump is an important one. And so, in my opinion, it is important that occupational or industrial hygienists know the requirements, not only for use, but also, for example, if you want to purchase or rent equipment. And because not all pumps that are available are meeting the requirements for measuring particulates, for example, or metals. And you should be aware of it. And so there is an international standard on this where the requirements are in there. I will go a bit fast on the slides. They are all in there. What are the most important one you have to take into account? But I have to say that, as the presentation will be shared, you can go through it, for yourself to look at what you try to find out. But I will go to the most important one. And so, you know that it should have an automated control that keeps the flow rate nominally constant, and that is important, nominally constant. What I also see in many cases that people are just looking at the screen of the digital pumps now. They see 2,200 milliliters a minute, and that is what they're writing down. And at the end of your sampling campaign, you will see that it is still 2.2 there. But in the meanwhile, what is happening in the background is electronically, your flow rate has been deviated from the initial one because he tries to maintain, let's say, a constant flow. So you need to be aware of that. And if you test it, you will see that it will deviate. And you cannot just write what is on the screen of a pump. That is a completely wrong flow rate. So failure indicator, and it should shut down when power consumption becomes too high, which also means that if you have a too high back pressure, you will hear it in many cases for people that have taken samples already. You hear actually when a pump has a very high back pressure and will shut down in a few minutes probably. Well, here are, let's say, the weights that are described. So, please take this into account. This has to do with the ergonomy of the worker carrying your sampling trains. And, you should have a maximum operating time, at least 1 hour, and preferably above 8 hours to make sure that you can measure, let's say, your reference period for limit value. And here the pressure drop should be, let's say, for 1.6 kilopascal at 2 liters a minute, with a maximum flow rate below 5 liters a minute. And your flow rate must not deviate more than 5%. That is what I mentioned already earlier. So when it's blocked, the pump should shut down. And it may automatically attempt to restart. So the new ones are doing that actually. They shut down and then restart, which actually happens in the background. And so the flow rate has been adapted to make sure that it can handle the back pressure. So also, at the temperature is important. And so, if you go down, for example, to 5 degrees Celsius, it should not also deviate more than 5%. And in many cases, the requirements of pumps are stated between, let's say, 5 and, the new ones are 45 degrees Celsius. But if you are outside, let's say, the temperature range, meaning below 5 degrees Celsius and higher than 45 degrees Celsius, the pump manufacturer cannot guarantee you that you will have no deviation that is lower than 5%. And in many cases, you will see that this is actually true if you are outside the temperature boundaries. So pulsation, this is another one, and I mention it very specifically here because any sampler dealing with particulate sampling is depending on pulsation of flow rate. And so you should ask, if you use certain pumps, and that their pulsation is not exceeding 11% of the average volumetric flow rate. And I can tell you, maybe for people who are interested, I can send some links to the papers that are written around that. There are quite a lot of pumps that are better not used to measure particles. And so just be aware of it, that are actually have a pulsation flow that is higher. And what actually happens if you have a pulsation flow that is higher, the dust particles are actually going off your filter because of that pulsation of your sampling substrate into your sampler. And so you have a serious estimation of the real exposure. A second requirement is related to the sampling substrate, where you will see, depending on substrate type, that you will have weighing stability issues, hygroscopicity, background concentrations of chemicals, and specifically metals and metalloids. In many cases, for example, especially chromium-6, but also lead. If you use a PVC filter and you want to go to very low lead levels, well, that's probably not the best filter to use, because there is a quite high background of lead in there, and the same for chromium-6. And so be aware of it. You cannot just use any substrate in your sampler, or one that you find somewhere, to measure metals and metalloids. And you also should take into account that it will have an influence on the sampling efficiency of your sampler. I will come back to that a bit later. And take into account that it can react with extraction agents. For example, if you use speciation protocols for metals and metalloids, you do know that probably in your country, well, in Europe, this will disappear, and happy about that, because speciation is an issue. But in many countries, you still have, for many metals and metalloids, soluble and insoluble limit values. And meaning that, that means that you have to use a speciation protocol to determine the soluble and insoluble part. And, well, for example, also for welding fumes, you can have spinels, which are actually minerals with a specific metal oxide or sulfur anion. And they are very difficult to dissolve with normal acid mixtures. Meaning that your normal protocol that you use, for example, in your lab, or the lab you work with, for, well, the normal range of metals, is in many cases not applicable if you want to determine metals in welding fumes. If I ask that question to many occupational hygienists, do you use another method for welding fumes? Well, the answer is 99.9% no, which is, well, not really a good investigation of your procedure. And because we have seen that it has a serious underestimation of the real metal exposure in welding fumes. So you should take this into account. Well, for gravimetric analysis, many people are still, and I think if we do the survey to everyone that is here, we will probably find out that many people are still doing gravimetric analysis and metal analysis on the same substrate. Well, you should be aware of a few things. There are quite a lot of slides explaining what you should be aware of. But, for gravimetric analysis, you have an influence of static charging, relative humidity, temperature, and air pressure. And static charging, for example, you should be elimination, well, when you do the procedure. So this is something, if you do your investigation, that you have to ask your lab, how do they do that? And so then you have to discharge, weigh, and repeat this. Some research that is not published yet, but you will see what we have done, and we are in the final round of publishing that, showed that we have to minimum 3 times, well, we have to repeat this minimum 3 times if you weigh a sample to make sure that your uncertainty is below 50 or 30%. And the threshold, for example, if you use PVC filters, who are actually have most static charges. And so the threshold on your mass is 2 micrograms for a PVC. And if you use a disposable sampler PVC with the chimney included, it's 3 micrograms. So you can dissipate, let's say, static charge at higher relative humidity. I come back to that later as well. So if you put filters or sampling substrate 24 hours at 50% relative humidity, you dissipate also static charge. But the main issue is, if you do that at 50% relative humidity, you will have a serious issue if you want to measure hygroscopic aerosols. And there are quite a lot of metalloids and metals as well, whose aerosols are actually hygroscopic. So you should be aware of it, that, if you know that it is hygroscopic, and you, let's say, equilibrate your substrate at 50% relative humidity, you probably overestimate the exposure quite a lot. So be aware of that. So, well, what is the impact on relative humidity? So this is what we did, and what will be published. So, I'm not going into the details of the procedure, but you see actually that there is a difference, and this is important, in moisture uptake of many sampling substrates, and the moisture, let's say, well, the uptake and the moisture that goes out of the sampling substrate if you equilibrate. And actually, the difference between the uptake and the release of moisture is actually the hysteresis. And you will see that depending on the substrate you use, so glass fiber is here, and you see difference between 25 millimeter and 37 millimeter glass fiber. Here we have quartz fiber, PVC, and Versapor, which is actually a polyacrylate filter. And so you see, they all have different, let's say, uptake and release characteristics. So if you go to the IOM cassette, so this is the cassette, and you see, be aware of the fact that, this is in micrograms. And so you see at 50% humidity, the hysteresis, or the difference between the uptake and the release of water, is more than 1 milligram. And so, I'm always interested if people are showing me that they are measuring, let's say, aerosols gravimetrically, and that I see reports, for example, saying, well, there is 10 micrograms of dust if you measure the cassette and the filter. This is impossible analytically. And who is writing that in a report is actually lying. And this is showing why. And because you already have a hysteresis of milligrams. And so it's really difficult to go down to very low values. And this is, well, in general for metal cellulose ester, which we know is the best suitable filter for determining metals and metalloids. And because one of the requirements in the methodologies for measuring metals and metalloids is actually that your sampling substrate is fully dissolved before you do analysis. Well, a metal cellulose ester is very easily fully dissolved in very simple acid mixtures. But of course, if you use that filter also for your welding fumes, you will have issues because this is a gravimetric result. And so, we should be, as occupational hygienists, think more about our procedures and get rid of what have been done in the past. And so we are not living in the past. We are living today, and we have to make sure that we protect the worker in the future. And so, let's say determining metals and metalloids together with a gravimetric result, in my opinion, very difficult. Because you will have some issues there. So here you see, this hysteresis at 50% relative humidity, where you really see, for example, the IOM cassette is more than 1 gram, 1 milligram of difference, 1 milligram, 1.3 milligrams. And, equilibration time at different, let's say, humidity areas or regions are also included here. So you see, of course, PTFE, which is actually not at all hygroscopic, it has the shortest, let's say, equilibration time if you use it for a gravimetric analysis. The main issue will be that, bringing Teflon or PTFE into solution, well, this is really difficult because it's a very inert polymer, and, well, no acid mixture can dissolve a PTFE filter. And so you see already that it is an issue. It would be really good to use it, let's say, into the analysis. But for example, for chromium-6 it is used. But and there you can also determine the gravimetric analysis. But for other metal analysis, it will be really difficult to be used. And so you should be aware of it. And also, if you have very high equilibration times, this means that you will have some issues with the limit of detection and your uncertainty. Temperature and pressure. Well, the temperature, and this is also an important one, and the pressure affect the air density. And because it affects the air density, it also, well, it will have an impact on your volume and that you sample, and that's for sure. That's one thing. But it will also have an influence on the buoyancy of the filter during the weighing. And it's a quite similar effect as relative humidity. And so I put a formula in here, and that is just well, not for very general knowledge, but it's just showing that it has an impact, and the pressure, temperature, and humidity, and how it influences actually the weighing of substrates. And here you see what that impact is. And so what you see here, the right scale is actually so this is microgram, but you see if we use another scale because this is really milligram again, and this is because Casella-Higgins dual means that it is the full cassette, the Higgins dual cassette with the filter in. So that's like always in milligrams already, the influence. And you see, if you are, let's say, around the normal pressure, it's quite, let's say, the influence is quite low. But as soon as pressure changes, you can have quite huge influences. For example, for the Casella-Higgins dual, you can have an influence that goes up to, let's say, 3 or 2.8 milligrams of difference, just because of a difference in air pressure. And 2.8 milligrams is quite a lot. Here you see the influence of relative humidity, which is actually most constant at 50%, but deviates quite a lot if you're outside that boundary. And for temperature, this is room temperature. And as soon as you change your temperature, you will see how it will influence actually your sampling substrate, which will have an influence specifically, for any limit value that has to be related with a gravimetric result and related to metals and metalloids in many cases like welding fumes and so on. So yeah, I go past this one. So well, the next one is actually, the limit of detection and limit of quantification, where we measured a lot of substrates. So 5 sets of 10 substrates were reweighed every time. And then we calculated the limit of detection and limit of quantification. And actually, the limit of detection and limit of quantification is one of the major points that you have to investigate to calculate what minimum sampling time you need to measure against a limit value. And so if you don't know those values, you can never plan a measurement campaign. So here you see, depending on the substrates. So as I said, the manuscript is now almost finished and will be submitted soon. But you see here already what the difference is in limits of detection and limits of quantification depending on the substrate. And so, for example, if you want to measure welding fumes and metals, and you think you can do both together, and you use a metal cellulose ester filter of 25 millimeters, you need to take into account that your limit of quantification is 291 micrograms. If you then think about, the ideas that people have by lowering the limit value for welding fumes to 1 milligram per cubic meter, you will have serious issues to have a validated procedure. because 291 is higher than 10% of that limit value. And probably an MCE filter will not be the one that you will have to use for determining welding fumes. And the same for, you can discuss about, the DRS or the disposable samplers, which include wall deposits and so on, but still, they have quite high limits of quantifications. And if you want to measure inside, let's say, cassettes, like with the IOM, with a glass fiber even, that is a very stable filter. You see glass fiber is normally used for gravimetric analysis. But if you want to measure it into a cassette, you also see that your LOQ is higher than 10% of a limit value if, for example, the limit value for welding fumes goes to 1 milligrams. So, the choice that you have to make is depending on all those criteria. So here you see it in a graph where you are, and you see, MCE filters of 37 millimeters are really having, limits of quantification between 400 and 500 micrograms. And so, this is really difficult to be used if you have low limit values. Another thing in direct relation is the uncertainty, because we have seen in the beginning, and that's why I started with, saying my bias to standards. If you want to compare with limit values, we have to be aware that the uncertainty is a very important factor, and we have to be below a certain value. Well, here you see we have put the uncertainty of the complete procedure, taken into account sampling, sample handling, sample preparation, and analysis. And here you see all those different substrates. And so you can calculate, for example, the limit of detection and limit of quantification, but you have to take into account that your uncertainty should be below 50% if you want to go, let's say, at values at 10% of limit value. And so when we use those graphs, and you see here, if we, let's say, you see here the substrates with their specific LOQ, and to make sure that we have an uncertainty at 50%. And so, if you use, let's say, a PVC filter of 25 millimeters for some procedure, you have to take into account that you cannot measure lower than 59 micrograms as a mass on the substrate. And even at 59 micrograms, your uncertainty is plus minus 50%. That is actually what this means. And so, those are very important things to consider. Another thing to consider is the sampler. And a limiting factor in your sampler is your sampling substrate. And you see here, this is published. And so, if you don't take into account wall deposits, and I will come back to that as another limiting factor, the wall deposits, if you are not considering them and only analyze the filter, you will see that, let's say, the sampling efficiency will change depending on the substrate you use. And so the efficiency is positively correlated between the sampling substrate, meaning that actually, if you determine them gravimetrically, you will not have the same value, but the same ranges of values if you go to different pairs of samples. But you will see that you have statistically significant average difference in gravimetric results when using different sampling substrates. And so an MCE is capturing more particles than a polyacrylate, and a polyacrylate is even capturing more particulates than a PVC. So be aware of that. If you sample metals with a PVC in an IOM sampler, as an example, and you only analyze the filter, you're underestimating the exposure. And so, people start thinking probably in their own, oh, what am I doing? But you should be aware of it. And the main reason is, and especially for speciation protocols and so on, what is actually jumping off the surface of those filters are the bigger particles. And so, and the bigger a particle is, the higher the mass is of that particle. And so, and the higher the mass is, the more it will influence any further analysis. And actually, if you don't include wall deposits, you will have an issue because you haven't measured the bigger particles if you use, for example, a PVC substrate. Okay, so the next one is wall deposits. So there is an international standard available now that describe that how to include wall deposits into your analysis results. And this is really important for metals and metalloids, and because only analyzing the filters in samplers where it is known that they have wall deposits. Well, if you don't include them, you will underestimate seriously the exposure. And well, I have to say, when I go back to the initial slide, the first slide, the main reason is, and that's why I say that for 85 years, we were only interested in gravimetric results, and all samplers were developed for measuring the gravimetric results. And if you really go back to the initial papers of the sampler designs, you will see that, for example, the IOM sampler has been designed to weigh the cassette and the filter. It is only because we have never changed our mind in the last 40 years that we are still only, all of a sudden, that we decided all of a sudden, we will take out the filter because this is more easy to determine the metals if we want to dissolve it. Actually, it is wrong to exclude, let's say, the cassette. And so we need to be aware of it. So it depends on type of samplers. You have different ways of dealing with it. Disposable samplers are a solution. Wiping the inside of a sampler or a cassette is also described. Well, I have to say, and this is also a work that is still in progress and will be published. In my opinion, and this is my opinion in the research project, this is not feasible. We have tested it, and even we wiped 3 times, and we still had measurable quantities of metals. And so it is not a very good method. Rinsing is also described, but you should be aware that this is only applicable for insoluble materials. And if all materials are not dispersed in the solvent that you use or are stick to the, let's say, walls of a cassette or whatever, you have serious problems. You cannot use it. And it provides an extra layer of uncertainty, meaning that actually what I showed earlier in those graphs will change, and probably your limit of quantification will be a factor of 2 higher compared to, let's say, only analyzing the filter or using, let's say, disposable samplers. So you should be aware of that. Well, a requirement for the arrow sampler as such. So we all know the health-related particles where a sampler has to comply with. Well, we need to be aware, and I just mentioned it here, that new conventions are in preparation. And I think if I go to the next slide, I think most important are the orange and the thick red one. Because the orange and the thick red one are actually the new conventions that will come into play in the near future. So, the European standard is now already in a work item and will be probably published within a period of 2 years. And what should we be aware of is actually that the inhalable sampler efficiency is depending on wind speed in the workplace. And so we will have a different convention in low wind speed compared to the convention in medium wind speed. And you see, the thin red line is the old convention that we all know. This thick red line is medium, let's say, wind speeds, and the orange line is in low wind speeds, the convention. So meaning that, we should also test samplers, let's say, differently as we used to do it in the past, because we have a new inhalability curves of particulates depending on the wind speed in the workplace. And it's mainly, let's say, the inhalable sampler that will have that is very depending on the wind speed in the workplace. Well, the thoracic and the respirable are changing slightly, and the main reason that they change slightly is because in the past, or in the old inhalability conventions, they were actually calculated out of the inhalable fraction. Now they have their own conventions. And for people who want to know that, if you use a real-time device that tells you, that measures the PM10 or PM4, and people are saying, well, PM4 is the same as respirable. Well, here you see PM4 is not the same as respirable. It is another convention. And PM2.5 is also another one. And PM10 is very close to the thoracic convention, but still not exactly the same. But PM4 is definitely not respirable fraction. Be aware of that. Very important. Whatever people that are selling equipment are telling you. So, well, we always talk about aerodynamic diameter, just for people, who are in the beginning of the profession. I explain it a bit. And the aerodynamic diameter is a particle of a sphere of 1 gram per cubic centimeter density with the same terminal settling velocity in calm air as the particulate under the prevailing conditions of temperature, pressure, and relative humidity. So I already showed you what the influence is on weighing of all those parameters. All those parameters have also, and wind speed, you see in calm air here, wind speed has also an influence on the aerodynamic diameter. And so we need to be aware of the fact that the curves or the conventions are made within this ideal situation. Meaning, it's only actually completely applicable in the ideal situation. So, when do we have ideal situation? Well, you never have ideal situations. And so that's why you can have deviations depending on workplaces, aerosols you deal with, and so on and so on. And so, I think, well, Martin Harper is always saying that if you look at the catalog of people who are selling sampling substrates, you see more than 100 pages for volatiles of different sampling substrates and only half a page of particulate samplers and sampling substrates. Well, and that is the reason that there is only half a page is because during the last 40 years, we have never thought about it sufficiently. And we should be aware of the fact that it is not, let's say, the sampler that we are used to use or that are occupational hygienists that worked in the company 10 years before us. Well, we still use the same. That should not be the criteria. We should really think, what is the workplace? What is the aerosol we deal with? And then we choose our procedure. And you will probably have, if you have different, let's say, aerosols, different metals and metalloids, there is a possibility that you have to use different sampling substrates and different samplers even. And so that is what we need to, it's a mindset change. But I think, those webinars and training courses are actually have the meaning to have some training and sometimes mindset changes. So you see here what I said, the aerodynamic diameter is calculated for both of those substances. But you see clearly like kaolinite is like a more platelet particle. And hematite or iron oxide is more like a needle or fiber based particle. Well, it is clear and you can just test it. Take, for example, a pencil and throw it. It will fall differently as you take a paper and throw it and it fall, like the platelets. And so, even depending on this kind of, let's say, structure of the molecules that we are talking about, you will have already a deviation of the aerodynamic diameter or the way the particle behaves into the workplace and also behaves into your sampler. So here, well, you see, what we try to do is here you have the breeding system. And what we try to do is use a sampler and to get the same, let's say, particles that are going into, let's say, the deeper parts of the lungs or the respirable fraction, the upper part, the thoracic or nose, and let's say the complete upper part of the respiratory system as the inhalable fraction. Although, this is a wrong, I see that in many cases that it is presented like that. It is actually wrong because the inhalable fraction contains all particles that are going into the respiratory system. And the thoracic fraction contains all particles that goes into this system, and the respirable only all that goes into this system. Because the inhalable fraction also contains particle sizes that are part of the respirable fraction. So it's a bit of misunderstanding by deviating that. And I see that in many guidance documents and presentations as well. We should also change our mind a bit about that and not deviate it on the let's say samplers or fraction we sample use, but more deviated on the particle sizes we sample. And here you see then, let's say, based on, let's say, the particle size distribution, how much of the particle sizes that are actually part of all those conventions. And so, here you see how far they go. And that's why, also, well, one thing, and I just mentioned it, what I hate is that people always refer to D50. D50 is rubbish. D50 is only in theory very good. But it's more important if you talk about sampling conventions to indicate the range and not the D50. People are always saying, well, my sampler is sampling a D50 of 4 microns. Yeah, but what is the range of particles that he samples? If the range goes to 20 micrometers, well, you can still have a D50 of 4, but you are not within the respirable fraction. And so a D50 is not the one we really like to talk about. We should talk about ranges where samplers are operating in. So here you see the sampler requirements. So a lot of things are coming back. Here you see the uncertainty requirements are actually coming back even, for samplers as well, but even going back to the analytical procedure. And we should have an expanded uncertainty of the sampler that is below 25% all the time. And this is also, you should say, well, 25%, that's a lot. Well, it is really difficult to have, let's say, an expanded uncertainty of a sampler below 25%. So this is, well, in Word, what I said. And actually, for example, well, this is something that you will see in many cases when you buy a sampler, or at least you should ask your manufacturer to provide it to you. So those are bias and accuracy maps. And so this is showing you, if I use that sampler, how it deviates according to the conventions. So it shows you the bias related to the convention, and it shows you the accuracy to the convention. And so there will be no sampler that gives, let's say, 100% accuracy. This is impossible. They all deviate from the convention. But the bias is important because the bias is showing you how it is sampling certain particle sizes. And if you have an idea, for example, on what kind of aerosol you have in your workplace for metals and metalloids, it should be the bias map that helps you in choosing the right sampler for your aerosol in your workplace to make sure that you sample the real respirable fraction for your metals and metalloids. So now I will go very quickly through results from an international sample consortium study that we did with a grant of WorkSafe British Columbia. And so you see everyone who is involved here. And well, actually, we had some major findings. So this was, let's say, all work done in the laboratory and in the field, where we really compared samplers. And so, for example, you see here, when we did some lab exercises, we found aluminum cyclones give lower results compared to the PPI, and the PPI give lower results compared to the Higgins dual sampler, and the Higgins dual was comparable with the disposable respirable sampler. And so, well, you need to be aware of that, and because, this is actually the deviation. It's not exactly the deviation to the convention, but it shows already that probably, all those different samplers will have other bias maps to the convention. And we have tested this in 4 different workplaces. And even within 4 different workplaces, there was a difference, a same difference recognizable within the samplers. So, well, the problem is that, the European standard, 13205, describes that you have to use a reference sampler. Well, I think, the research within this grant study showed that there is no true reference sampler or reference method. And so, isokinetic samplers and so on, we need to be aware of it, and that it is not always, let's say, the best way of using. We had some problems with isokinetic samplers, specifically in calm air chambers and so on. It is really difficult to set up those exercises. We also find that the aluminum cyclones in Europe gave much lower results than the other samplers. And this was probably due to we don't really know what the reason was. But, it was all within the same lot of manufacturing those aluminum samplers. So probably we believe that there is something wrong with a lot of aluminum cyclones. And so, this is something I can definitely say that you will never find out if you have something like that. But if you start comparing samplers, you see, oh, actually, this sampler is not really a good one. The Higgins dual and the PPI gave similar results in the field. And this is different as in the lab, showing that probably a polydispersed aerosol in the workplace, gives, for example, for both samplers, more equilibrated results, and because probably they deviate, let's say, from the convention in the bias map just enough to equilibrate each other. And the disposable samplers taken into account wall deposits are consistently giving highest results. And this is already indicating something. It is indicating that many samplers have wall deposits. Although many people are saying, that respirable samplers don't have wall deposits, well, I don't believe, and they do have wall deposits. We have seen it in weighing. So, if you have cassettes and also PPI, for people who have ever opened a PPI, they probably have seen that there is also dust available on the polymer or the plastic barriers, boundaries of the sampler. So, the study for inhalable samplers, the major findings is that, this study confirmed many other studies that the IOM sampler have significant inner surface wall deposits. So they do not provide the ISO inhalable sample results if only the filter is analyzed. So be aware of that. Wiping the interiors, as I said, is really difficult. And, some indication shows that the existence of wall deposits may be concentration dependent. And so, if you really have high concentrations in your workplace, you will have, let's say, higher probability for having wall deposits. And, probably we have to investigate the data much more, but we believe that there will be a possibility to set some kind of threshold. So meaning also, if you are over the threshold, determining particles in your workplace, you better not use let's say, a sampler that has wall deposits. So you should use another one. And variability within the samplers are not allowing for accurate correction factors. So we also have seen in many cases that people try to use correction factors to compare one sampler to another. I don't believe in correction factors. Sorry. In my opinion, the in-between samplers variability is so high that you cannot really be, let's say, determine a correct correction factor. Well, overall conclusions, I think it's clear that aerosol sampling in workplaces is not yet as standardized as commonly perceived. I think I mentioned that already a few times. More research and funding is needed to produce more data, better standards and protocols for sampling aerosols, simple factors for normalizing is not feasible, and bigger exposure databases will suffer from sample bias and may get biased and noisy when you use data from different samples into your database. So I don't know how much time I have, Maharshi. I still have, I think,
You are doing a good job.
19 slides left.
So you have, if you would like to wrap up maybe in 5 minutes,
Okay, I can do that.
Stephen, then we can have a
Yes.
10 minutes of question answer.
All right.
Very interesting presentation, and I
Yeah.
will comment later. Yeah.
So, we also did a literature research. I will share, let's say, the information about that. We developed, or we are busy developing laboratory testing and for respirable and inhalable samplers for the new conventions. And here you see why it is important to do that, because we took the same sampler within 2 different labs. And actually, and here I am again with my D50 that I earlier said that is actually not the right metric. But you see the same sampler in 2 laboratories give a different D50. This is problematic. This is seriously problematic. Because it means that actually two protocols in 2 laboratories will give you another kind of sampler. But if you take it in your hands, it's exactly the same. So, yeah, that's why we need to do some more work on that. So, those are the things. So analytical procedures. So here you see, for example, the impact, let's say, for titanium dioxide. So this is just an example. Also, depending on your limit of quantification, your uncertainty plays a major role there. We already know that the sampler can have 25% of uncertainty. The sampling substrate can have 20 or more percent of uncertainty. The methodology can have, in this case, for example, 36% of uncertainty. So being below 50% of uncertainty, I think I'm not lying, as I said in the beginning, is really difficult. So be aware of that. So, well, here, conclusions on, let's say, real-time detection systems. Well, here, very important is, sensors. Real-time sensors only start measuring around 300 nanometers. Well, we should be aware of that. So everything below 300 nanometers is really difficult. And for nanoparticles specifically, well, are they measuring the complete nano object agglomerates and aggregates? No. Are they measuring agglomerates and aggregates? Yes. But agglomerates and aggregates are also part, in many cases, of the respirable fraction. So, something to think about. And here, the dependence of real-time detection system is mainly on the size distribution of the particles and the refractive index, or the color of the particles. And so if you have red particles, white particles, black particles, those will influence your number that is shown on your screen if you use a real-time device. And of course, real-time devices are very important in control management. And I just will show those 2 slides here, Maharshi, because the International Council on Metal and Mining have written the Health and Safety Working Group within ICMM, we have written a position paper on the use of real-time detection systems. You can find it with this link. And you see here that we actually saying that in another document that real-time detection systems have a huge impact in critical control management. And because, if you really want to have a good control for your metals or any particulate exposure, you can use real-time detection systems to evaluate, let's say, your critical control management system. So I have included here also the link where we describe actually a good practice. Well, it is a good practice guide on how to implement controls and critical control management into your workplace with examples and so on that you see in many cases in workplaces dealing with metals and metalloids. So with that, I think I just included some extra slides on some control options, but those are very readily available, and because it is not a very specific workplace that I'm talking about, but more general in metals and metalloids. And so you can download it, let's say, in many guidances as well, and because I used actually material that is available at the OHTA website in the course that you can download for free dealing on controls. So, but there are quite specific things, on particulate control systems that you should take into account. And thereby, I will leave it leave it to the questions, Maharshi.
Superb, superb. Stephen, I enjoyed so much the whole presentation. The work you have done is pioneering in terms of it's opening the eyes of many people. We have been collecting all the samples on which the major decisions are made, right? Whether to provide control or not to provide, whether to give a respirator or not to give a respirator. I'll give more comments later, but let me see the comments. We have a Donatella Dennis. The question is, what do you think about Lippmann cyclones? Stephen?
I always say one thing to myself. It is really difficult, let's say, to say something specifically on a manufacturer of a certain device. I don't like to do that. And because, they're all designed with a purpose. And probably, like I said earlier in the presentation, the purpose will depend on what workplace you have. And probably this cyclone will have a place in a certain workplace with a certain aerosol. And definitely what we should take into account and remember all the time is that probably if you only have one cyclone available, that it will not be suitable for any workplace we are sampling. Is that a good answer or?
That's right. Right. Any other questions? Why don't you leave? If you would like to unmute, I have a question. Yeah, go ahead, please.
Thank you.
Yeah.
It's clear. It's clear.
Very nice, Donatella.
I've used for silicon in
Yes.
tails, ceramic,
Yeah.
Nice.
And is too dry fraction,
Yeah.
Is 2-3 is the curve of respirable fraction, and that is good for silicon.
Yeah.
In that industry.
Yeah, well, maybe it is. Yeah. Well, the thing is, if you do risk assessment, for example, and now, I know it's another way of thought, and it's probably also another school of thoughts, and because, like Maharshi said, our decisions are based on an outcome or a number, but we need to trust that number, and what we forget is actually that we should pre-investigate quite a lot to make sure that we can trust that number. And what you say, Donatella, I can completely agree. I don't know, actually, I should go look at it a little bit deeper into the detail on the specific sampler you mentioned. But for example, if you determine the particle size distribution within a workplace that is dealing with ceramics, and you see, for example, that the range of the particle size distribution is quite close to the curve or the bias map of the sampler, well, it's a perfect sampler.
That's our idea as a technique. Yeah. Thank you. Thank you.
Very good. I'm happy you understood what I was saying today.
Thank you. Thank you.
Yeah. Any other questions you can put in the chat section? I'm keeping an eye on the chat box. Also, if you would like to speak, you can raise the hand, unmute yourself and talk. I have a few thoughts, which first of all, Stephen, pioneering research work. In every place where we talk as a hygienist, we say that the decisions that you are making, health of the people depends on the decision that you make, whether the exposure is acceptable or not. Now, if the variability is so significant that we are learning, I don't believe we have ever addressed, and I'm telling you with my 300 workplaces in 30 countries and looking at 10,000 data sets, we have never thought about having a pressure and temperature variability for the collection efficiency. No one even closely have considered.
I know.
Right? It has not been even discussed at any place of such an important matter, because if your collection efficiency is not there, what is lab going to do the analysis? Right? Lately, the pharmaceutical industries have realized with IOM sampler, because they were doing lots of IOM sampling about the wall deposits. Some studies have been conducted by several pharma organizations, and conclusion was similar to yours. Pharma, it's even more challenging when your limits are in nanograms per cubic meter for high potent compound, to make sure that wall deposits doesn't account for loss of the particulates when they do the analysis. And so I was making some note while you were talking. Right. The wall deposit was one thing. And so in situ extraction has been done, where you don't open, you just pour your solvent or whatever media in which you would like to, and don't open the cassette. And in fact, we need to tell the laboratory to do that. They should not be opening the cassette, right, Stephen?
Yeah, but that's fine. For example, for certain pharmaceuticals, but also for some soluble metals, for example. For nickel, well, just an example, for the soluble methodology for soluble nickel, for example, you use citric acid. Well, citric acid is dissolving all soluble nickel. And so meaning, if you know that, well, then it can be used. I mean, you're quite sure that everything will be in solution. And if you analyze the solution, you will have everything, including wall deposits, if you do in cassette extraction. But this is not the case for all, let's say. We should be aware of that. The solubility of a substance is depending on that.
Right. And 25 degrees centigrade is the perfect temperature at which the cyclone collection efficiency is optimum when I was looking at one of the chart. Now, invariably, we go to foundries, a steel plant, and smelters, and do the metal sampling or dust sampling or total particulate sampling using all, where the temperatures are often invariably more than 25 degrees.
Yeah.
And again, which has never been considered, never been thought of. So this is indeed a pioneering work. I would like you to spread this message, and we'll help you to spread this message as much as feasible to the IH community around the world. And in the process, help the hygienists and help the people to whom we would like to protect.
Yeah. No, thanks,
Any other
Maharshi.
questions? We still have time. Oh no, God, Stephen, this is, I mean, we have had lots of discussion on a number of other subjects, but this is the first time I'm listening the work that you have done and seeing the work that you have done.
Well, not alone. And there are
I
many people
understand, of course,
involved.
but we need a leader who can drive the
Yeah.
agenda, who has a passion.
Yeah.
And we all have a passion.
Yeah. That's my passion. I have to admit.
You can see it in
yeah.
this voice also. uh, everyone, any comments, question? Hmm? And I was going to send a message to our association members in India and other places saying that in our professional lifetime, our job is, can we go beyond just thinking about collecting the sample, analyzing the sample, giving the results, and keep doing this over and over again, as opposed to just spending at least 20% of time thinking about what is it that we are doing. Do we have a confidence in what we do?
Yeah.
Mm-hmm.
I believe that should be, and that's why I created that let's say time frame, because it's clearly that all of a sudden samplers were developed, and what and well, in many jurisdictions they still call industrial hygienists pump jockeys. And from that time on, everything was available, and just anyone was running around to sample.
Telling you.
And I think that is the main issue. We forgot
It
to
is.
think. Yeah.
It is such a major issue. I keep saying, and with John Mohosen, and we have been talking about 50% of the data sampling that we are collect, and this may sound very strong statement, is a worthless.
Yeah.
In addition to the anomalies that Stephen talked about, there are a number of factors that we don't consider. HCl has a ceiling limit of 5 ppm, and we collect sample for 8 hours and come to the conclusion. Right? A task duration is for 8 hours. We collect 4 hours sample and never think about there may be exposure after the sampling duration and conclude the TWA.
Yeah, that's true. That's true.
And happens all over.
Yeah.
So let's hear, Saleh, from what we hear, I believe the biological exposure indices are alternative, good options whenever possible. What do you think?
Wrong. Well, that's a wrong thought. It's a wrong thought, especially as an industrial hygienist, because one of the major issues. Yeah, it's too late. You already have it systemically, so it is a combination of both. And actually, to be honest, what I experience, if I tell my story, and I think it's I don't know, but many people are saying, well, if you say all this, why are we still measuring exposure? I'm not saying that we have to stop measuring exposure. I'm saying that we have to think before measuring exposure. And that is something we forget, to be honest, in general.
Right, and not for sharing point, but for the assurance. Can we do that?
Yeah. At the end of the, I think, when the whole assessment has been done, from the exposure risk assessment through the measurements, you have sufficient data and so on, you have the controls in place. Well, I think from that point on, it is interesting to do both.
Absolutely. This was very interesting webinar, Stephen, and all of us would like to thank you. Yeah, Donatella, please, we have a time.
I think when you do the biological exposure indices is for skin contribution. Also, I mean that you can both estimate, and when you use particular metals and metalloids, it's quite important to make a sort of calculation. Yes. Because it's a calculation, there are approximation. What is skin contribute? Sometimes it's very important for my experience.
Yeah, sure, and I agree. I think, of course, the theme of this presentation was inhalation exposure assessment of metals and metalloids. What I haven't covered, but I'm also quite involved in it as I'm convening working group 8 at ISO level on dermal exposure assessment. And of course, we cannot forget that there are methodologies for surface levels for metals and metalloids. There are, let's say, well, for example, the TLVSL, surface level TLV, has now been incorporated mainly for organic substances, but probably there will be, let's say, TLVSLs for metals and metalloids as well in the future. And all those things combined are actually the complete exposure profile of a worker. And so, but I'm focusing here on the inhalation exposure, which in many cases is the one that we, well, don't break open my mouth if I start talking about exposure assessment of surface and skin, because the uncertainty there is even worse, and methodology. So I think inhalation exposure is the one that we do best momentarily, although there are still some things we need to think about, but we are the others are even worse, the other exposure routes.
Excellent. Hey, everyone. We appreciate very much the time. We had one point in time 46 participants or so. I was making the numbers here, 43 participants. So thank you so much. I would like to encourage you. We will be offering more webinars. If you have specific topics or a speaker that you would like to have offer the webinar through IOHA, by all means, please let me and Rita know. So Stephen, thank you again. Thank you all the participants. Rita, thank you for all the coordination and planning. Okay. Any other questions?